This is the Earth Science Classroom. Welcome back to the channel. This video is all on the anatomy of an earthquake, looking at all the terms that are associated with earthquakes and how we understand when an earthquake occurs and how we can move into topics like seismic waves and the eventual damage and hazards that earthquakes cause. So first we have a block diagram. We have a simple three-dimensional block here. We use this to isolate a certain rock to show you what's going on within the crust. Rather than showing the entire crust as a large unit, we kind of break it down and look at a single rock block profile, just like we do with the atmosphere, looking at a parcel of air. So we have here this fault line, and the fault line is in this case diagonal, so it's going to be a dip slip, which shows the angle between the horizontal plane and the fault plane, and this would mean there would be two sides of the rock block diagram, which we have to then identify, which is the footwall versus the hanging wall. So the quick technique is to apply a nice X anywhere along the fault line, the fault plane, and draw vertical arrows down, and whatever side it is, this will be the footwall, and the other side will be the hanging wall. Or you could draw a person, a stick man, and the feet are on this side of the rock profile, therefore this would be the footwall. Then we can figure out which way the hanging wall is moving, and that would dictate the type of dip slip fault we get, either normal or reversed or thrust, or even if it's an oblique fault, which will have two distinct movements. If it was a strike slip, this fault line would be vertical. In terms of the anatomy, if we put another X marks a spot, and this is the exact place of where the earthquake happens or earthquake occurs. This is called the focus or the hypocenter. Now this is at a certain depth under the ground, and some literature, some textbooks, say that there is a defining point or depth at which where the earthquake occurs, which would define whether it would be a shallow or a deep earthquake. Now some literature says as little as 15 kilometers, some say between 45 to 70 kilometers, and it's a range between those numbers, which would constitute a shallow earthquake. If it's a deep earthquake, it can usually go down as deep as 700 to 800 kilometers under the ground. The surface, however, this would be related to subduction zones in various different angled subduction areas around, let's say, the Pacific Ring of Fire. But let's say this is the surface. I draw my stick man on the surface. Now, depending on how shallow or deep the earthquake is, will give an indication how much energy and shaking will occur on the surface. The deeper the earthquake, generally, the less the surface is going to feel. Whereas the shallower earthquake, the earthquake that's closer to the surface, that would generally give a more destructive, more energetic result on the surface. Now, why is this? Well, because it goes towards the surface, and it's a shallow earthquake, the surface waves that are going to transmit up to the surface and then resonate and propagate through the surface, both the L and the R waves, these will be more concentrated energy if the earthquake is shallower and closer to the surface compared to a deeper earthquake where the waves have to initially travel up a great distance towards the surface in order to then pass through and transmit and resonate and propagate through the surface, causing the damage. Now, if I take the focus or hypocenter, if I go straight up vertically from that point along the fault line where the earthquake happens, and the energy is released as seismic waves, the elastic energy buildup, if I go straight up vertically onto the surface, there'll be a point on the surface that is directly above the focus or hypocenter. This is called the epicenter, and we use this for usually maps and locations because the fault line is obviously underground, therefore the focus and hypocenter is underground, and generally you get this certain depth of the earthquake occurring. However, the epicenter is always on the surface and can be used as a locating tool for maps. Now, the important thing for the seismic waves are they are transmitted or released in all directions throughout the rock medium, whether crustal rocks or upper mantle rocks. Now you have the P wave and the S wave. They're both body waves going to go through the body of the Earth. Now the S wave does not go through liquids, but we have this resonating energy field or energy waves going through the layers. And as I mentioned before, you have this resonating surface waves coming up to the surface and then going through the surface, causing damage, which is the L and the R waves. And the direction of movement we call propagation. So the energy or the particle motion, the way the particles move through energy and through the process of transmitting energy through a solid, liquid, or gas material is called propagation. So from here we can link in the P&S time travel graphs. We can link in different kind of waves and what they are, the P, S, L, and R. We can link in the aftershock, the foreshock, and the elastic rebound theory to explain how these earthquakes occur. We can link in the different kind of hazards and liquefaction and tsunamis and different locations where these earthquakes can occur, case studies and examples of deep earthquakes versus shallow earthquakes, and looking at different locations that have experienced very large earthquakes, like Sumatra in 2004, like Japan in 2011, like Alaska in 1964, and the two earthquakes on the San Andreas fault line, both in 1989 and 1906. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.